Let's explore some fundamental electrical concepts. Electricity involves the flow of electric charge. Voltage, often described as electrical potential difference, is the force that drives the electric charge, known as current, through a circuit. It's measured in volts. Think of voltage as the pressure pushing water through a pipe. A higher voltage means more pressure and therefore more potential for current to flow. Current is the rate at which electric charge flows. It is measured in amps. Using the water analogy, current would be the amount of water flowing through the pipe per unit of time. A higher current means more charges moving through the circuit. Resistance is the opposition to the flow of electric current. It is measured in ohms. Resistance is like a constriction in the water pipe, making it harder for the water to flow. A higher resistance means it's more difficult for current to pass through a circuit. These three quantities, voltage, current, and resistance, are related by Ohm's law, which is expressed as voltage equals current times resistance, or volts equals amps times ohms. This fundamental law is the cornerstone of electrical circuit analysis. If you know any two of these values, you can calculate the third. For example, if a circuit has a voltage of 12 volts and a resistance of 6 ohms, the current can be calculated as 12 volts divided by 6 ohms, which equals 2 amps. Another key concept is electric power, which is the rate at which electrical energy is transferred or consumed. It's measured in watts. Power is calculated as voltage times current, or volts times amps. Using our previous example, the power consumed by the circuit would be 12 volts times 2 amps, which equals 24 watts. Circuits can be configured in two basic ways: series and parallel. In a series circuit, components are connected end to end, forming a single path for current to flow. The current is the same through all components in a series circuit, but the voltage is divided among the components. The total resistance of a series circuit is the sum of the individual resistances. For example, if you have 3 resistors in series with resistances of 2 ohms, 4 ohms, and 6 ohms respectively, the total resistance would be 2 ohms plus 4 ohms plus 6 ohms, which equals 12 ohms. In a parallel circuit, components are connected side by side, providing multiple paths for current to flow. The voltage is the same across all components in a parallel circuit, but the current is divided among the components. The total resistance of a parallel circuit is calculated differently. The reciprocal of the total resistance is equal to the sum of the reciprocals of the individual resistances. The formula is 1 divided by R total equals 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3, and so on. For example, if you have 3 resistors in parallel with resistances of 2 ohms, 4 ohms, and 6 ohms respectively, the total resistance would be calculated as follows. 1 divided by R total equals 1 divided by 2 ohms plus 1 divided by 4 ohms plus 1 divided by 6 ohms. This simplifies to 1 divided by R total equals 0.5 plus 0.25 plus approximately 0.167. Therefore, 1 divided by R total equals approximately 0.917. Taking the reciprocal of both sides, we find that R total is approximately 1.9 ohms. Understanding these basic concepts is crucial for anyone working with electrical systems. Voltage provides the driving force, current is the flow of charge, resistance opposes the flow, and power describes the rate of energy transfer. These concepts are governed by fundamental laws such as Ohm's law and the power equation. The type of circuit, whether series or parallel, affects how voltage, current, and resistance behave. There are also additional concepts of alternating current and direct current. Direct current, or DC, is a type of electrical current that flows in one direction only. It is typically produced by batteries in electronic power supplies. Alternating current, or AC, is a type of electrical current that periodically reverses direction. It is the standard form of electricity used in homes and businesses. The frequency of AC is measured in hertz, which represents the number of cycles per second. In North America, the standard frequency is 60 Hz. The voltage and current of AC waveforms are typically sinusoidal, meaning they vary in a smooth, repeating pattern. The root mean square, or RMS, value of an AC waveform is a measure of its effective voltage or current. It is the equivalent DC voltage or current that would produce the same amount of power. The RMS voltage of a standard 120 volts AC supply is actually about 170 volts at its peak value. Transformers are used to step up or step down AC voltages. They consist of 2 or more coils of wire wound around a common core. The ratio of the number of turns in the primary coil to the number of turns in the secondary coil determines the voltage transformation ratio. For example, if a transformer has 100 turns in a primary coil and 10 turns in the secondary coil, the voltage will be stepped down by a factor of 10. Electrical circuits often include capacitors and inductors. A capacitor is a device that stores electrical energy in an electric field. Capacitance is measured in farads. Capacitors oppose changes in voltage. An inductor is a device that stores electrical energy in a magnetic field. Inductance is measured in henries. Inductors oppose changes in current. In AC circuits, capacitors and inductors introduce reactance, which is the opposition to the flow of current due to capacitance or inductance. Reactance is measured in ohms. The total opposition to the flow of current in an AC circuit, including both resistance and reactance, is called impedance. Impedance is also measured in ohms. Understanding basic electrical safety is of utmost importance. Always disconnect power before working on electrical circuits. Use insulated tools and wear appropriate personal protective equipment. Never work on live circuits unless you are properly trained and authorized to do so. Be aware of the potential hazards of electricity, such as electric shock, arc flash, and fire. Follow all applicable electrical codes and regulations. Grounding is an important safety measure that provides a path for fault current to flow back to the source, tripping a circuit breaker or fuse and preventing an electrical shock. Electrical wiring must be properly sized to handle the expected current load. Overloaded circuits can overheat and cause fires. Use appropriate wire gauges and circuit breakers or fuses to protect against overcurrent. Electrical codes, such as the National Electrical Code or NEC, provide detailed requirements for electrical installations. These codes are designed to ensure the safety of people and property. It is important to consult the NEC and other applicable codes when designing and installing electrical systems. Electrical components are typically rated for specific voltages, currents, and power levels. Do not exceed these ratings, as it can damage the components and create a safety hazard. When selecting electrical components, consider the application requirements and choose components that are appropriately rated. Electronic circuits often use semiconductors, such as diodes and transistors. A diode is a semiconductor device that allows current to flow in one direction only. A transistor is a semiconductor device that can be used to amplify or switch electronic signals. These components are essential for building electronic circuits and systems. Understanding the basics of electricity is essential for anyone working with electrical or electronic systems. By mastering these concepts, you can safely and effectively design, install, and maintain electrical systems. Always remember to prioritize safety and follow all applicable codes and regulations.